and we have the following property as well. So first of all, like in additions, like the order doesn't matter. Okay, you can put A plus B or B plus A, it doesn't matter. Okay, and if you have the parentheses here, it doesn't matter as well. You can put B and I mean like you can sum up B and C first and then plus A, or you make the calculation, you add A over B first and then add C. That doesn't matter. Okay. And also we will have a spatial matrix which is called zero matrix. In that matrix, all elements in that matrix are 0. So in that case, no matter which matrix you add with, then you will get the original matrix here. Okay, so that is the property for additions. And for the scalar multiplications, it should be quite intuitive. Order doesn't matter. You can put it in the front or in the back, right? And you can do it distributed rule. So you can do like first you add up A and B and then times a small c here, or you can first do the multiplication, like get the CA and CB and add it up. Okay. Or here, just the negative number. It's like the negative A is like you times, you multiplied the matrix A with the negative number 1. Okay. Then the multiplication. So here the order matters. Okay. Which means that you cannot say A times B equals B times A. It is not always true. Okay. So I put here in most cases. Okay. But if you looking at some cases like this one, like A times parentheses B and C, so it doesn't matter if I did the multiplication for AB first and then times C. That doesn't matter. And meanwhile, you can do the distributive rule. Okay, so let's say that first you can do like B8, the addition between the B and C, and then times the multiplication, times the matrix A. Or we can do like the multiplication between A and B and A and C and add them up. Just be careful that when you do the distribution rule, you cannot switch the order. So if you put it on the left hand side, then this A must appear in the left hand side. Okay, and if A is on the right hand side, then it's the other way around. A should be appear in the right hand side. Okay, so that's the idea. Okay. Right, then once again, linear transformations. What do I want to say here? So we can actually define functions t that is from n dimension to m dimensions in this following way. Okay, so multiplication. So I think here I do it m like the matrix n by n and times the matrix n by p. But now I only want to focus on only one dimension single vectors here. Okay, so this is the matrix multiplications if we only have the n by 1 vectors here. I mean, actually you can do like n by p as well, but for the purpose of illustrations, I think this is much easier to see. Okay, so we already told, I already told you how to do the matrix multiplications here, right? So following the definitions, you will get the n by 1 vectors here. You do the first elements, how to get it. You take the first row of matrix A and do the dot products with the vectors x here. You get the first elements, and you can do the same from the second row of the matrix A and get the second elements to get the last one. Okay, and I want to talk a little bit more, which is my preferred way to look at the linear the matrix multiplications. So actually we can take that as the linear combinations of all the columns in matrix A. So I just kind of like decompose the calculations here, right? And write it out in this way. So here you can see that this is actually the first columns of matrix A, second columns, to the nth columns. And you can times the first elements in the x vectors here and times the second elements of x vectors and to the nth vectors, and you add them up, you will get the same result. So this is actually a linear combination of all the vectors in matrix A, right? Okay, right, and because we already showed that linear combination is a linear transformation, so actually it satisfies these two property. Okay, right. Yeah, so I already told. So this is the illustration here. Okay. Right, transpose. Okay, so you flip the same thing twice, you'll get the original stuff. So like A transpose will get A. Okay, and you transpose something like A plus B, then it actually equals you transpose A and transpose B and then add them up. It doesn't matter. Okay, and this is something you want to pay attention to. So when you do the multiplications and then do the transpose, it actually equals you do the transpose first and you reverse the order here. Okay, so you are going to use this quite often in your proof. So make sure that you didn't mess it up. Okay. Then it's the trace. Yeah, it's just the definitions here. Right. Don't think there's anything I want to add here. So